Now let us study what is called as the sigma notation, which is a very powerful and compact notation to denote the long sums of a series which involves many terms. So that means suppose we want to refer to this particular sum, that is say term 1 plus term 2 plus term 3 and so on up to say term number n. Now rather than writing this entire expression every time, this can be written in a compact notation like this. So here we write the Greek letter sigma and we write a generic term, that is tr, where r is a kind of counter, that is it takes the values from 1 up to n and in the steps of 1 only. So therefore here we write below sigma that r starts with 1 and it goes up to n and in the steps of 1, so that is after 1 it will take the value 2, then 3 and so on up to n. So this is a short notation for referring to this entire expression. Now in many sums it is understood that the r will start with 1 and it will end with n. So in that case we may just write the summation as tr. Alright, but it is not a general rule because it may depend on the question. So it is important to keep in mind the data given in the question and only then we can decide whether we are to skip writing the limits of r or not, because sometimes there might be some question in which we may have to write the range of r as say something like say r starts with 10 and ends at 20. So in that case it is absolutely important to specify these limits, but sometimes it is not required and we can generalize. Alright, now let us move ahead and using this notation let us derive 3 very important results and also study the properties of sigma notation. So here are a few simple properties of sigma notation which we will use to derive the results. The first property is, if we have the summation of k into tr where k is some constant, then that constant k can be taken outside the summation. So therefore that will be equal to k into summation of tr as r goes from 1 to n. The second property is summation of 1 as r varies from 1 to n is nothing but equal to n. Now this is evident because we have to sum 1, that is nothing but every term is having the value as 1 itself, isn't it? So therefore 1 will occur n times and hence therefore we see that this total sum is nothing but 1 added n times, that gives us n, right? And the last property is summation of ar plus br in bracket is equal to summation of ar plus summation of br. So that means since summation basically is nothing but addition and we have the addition operation inside the bracket, so therefore both are conformable to each other and therefore we can split the summation as shown on the right hand side. Now let's move ahead and see 3 important results. The first one gives us the sum of first n natural numbers. Alright, so that means we have to find out the formula for doing the sum of 1 plus 2 plus 3 plus so on up to some natural number n. Now to find out this we start off with one identity that is given by x plus 1 the whole square minus x square is equal to 2x plus 1. Now we can expand the left hand side and easily confirm that it gives us 2x plus 1. Alright, now since this is an identity, it just means that it is true for any value of x. So what do? We start putting successively different values of x starting with x equal to 1 and get the corresponding equation. So x equal to 1 gives us x plus 1 the whole square, that is 1 plus 1 the whole square, which is 2 square minus 1 square is equal to 2 into x, which is nothing but 1 here, plus 1. Alright, Now let us put x equal to 2 and write it as 2 plus 1 is 3, so which gives us 3 square minus 2 square is equal to, on the right side we have 2 into 2 plus 1. Let's write one more and then we will generalize by looking at the pattern. So here we have 4 square minus 3 square is equal to 2 into 3 plus 1. Now continuing this, we can put finally x equal to n, and here we will get n plus 1 the whole square minus n square is equal to 2 into n plus 1, right? Now suppose we add up all these equations, that is from here to here, right? You will see that on left hand side, say 2 square will get cancelled, 3 square will get cancelled, so is 4 square, and so on up to the last term to get cancelled is n square. So what remains on left hand side is n plus 1 the whole square from the last equation, and we have this 1 square which is nothing but 1 from the first equation. Now on the right hand side, if you look at the first portion, that is each term on the right hand side, the first term is 2 into the counter, that is 2 into 1 plus 2 into 2 plus 2 into 3 and so on. So therefore what we can write on RHS is nothing but 2 into bracket 1 plus 2 plus 3 and so on up to n. This is the last number to add. And now if we consider the second part, that is nothing but all the ones which are added for n times, because there are n equations. So therefore addition of 1 for n times gives us n itself, right? So now therefore simplifying this further, on left hand side we have n square plus 2n plus 1 minus 1 is equal to, we have 2 into, now this entire bracket that is present here is nothing but the sum that we are interested to find out. So let's denote that entire sum as, say, s, and plus finally we have n. Alright, so on left hand side 1 gets cancelled and we can write 2s as nothing but n square, and n will get cancelled from 2n, leaving only n. So therefore s is nothing but, from the numerator we can take n common, keeping n plus 1 in the bracket, and the 2 will be dividing. So therefore finally we get the required sum as n into n plus 1 whole upon 2, alright, which is the required sum. So let us denote this by sigma notation as the summation of r, as r varies from 1 to n, is given by the formula n into n plus 1 bracket complete whole divided by 2. This is a very useful result and we need it to use in many examples. Let's go ahead and derive a similar result. Now instead of adding the numbers, here we want to find the sum of squares of the first n natural numbers. So that means what we want to find is, here let's denote that s by 1 square plus 2 square plus 3 square and so on up to n square, right? Now here the procedure is essentially simple as what we used in the previous. So instead of the identity of x plus 1 the whole square minus x square, what we will use is x plus 1 the whole cube minus x cube. Now on expanding we will realize that x plus 1 the whole cube gives us x cube as a first term, which will get cancelled with this particular x cube. Now the second term in the cubic expansion is nothing but 3x square. Then the third term is 3x, and then finally we will get 1 as the last term, which is 1 cube. Alright, so here after also we follow the same procedure, that is we put x equal to 1 and get a relation, then we put x equal to 2 and get another equation, and so on. And finally by adding all the relations, lot of terms will get cancelled, and then on further simplification and bringing together all the like terms, we finally get the required sum as, so here we write summation of r square, as r varies from 1 to n, is nothing but n into n plus 1 into 2n plus 1 whole divided by 6. Right, so that is a formula to find out the sum of squares of first n natural numbers. And now let us see the sum of cubes of first n natural numbers. So here let us write the formula directly. Once again the procedure is similar. Sum of r cube, as r varies from 1 to n, is given by n square into n plus 1 the whole square whole upon 4. Now if you observe this closely, no doubt this is the formula for sum of cubes of first n natural numbers, but we can rewrite that in slightly different manner. That is, we can consider this expression as n into n plus 1 upon 2 the whole square, isn't it? It's the square of this bracket. And if we recollect, the expression which we have written inside the bracket is nothing but sum of first n natural numbers that we just did some time ago. So that is nothing but square of sum of first n natural numbers. So the sum of cubes of first n natural numbers is square of sum of those n natural numbers.